Hello everyone, welcome to this 24th session on experimental methods in thermal engineering. So in our last lecture we couldn't complete our discussion on the measurement of velocity. Okay, so in this lecture we will try to see some of the few techniques which we have not covered yet and are mainly employed for measurement of velocity nowadays. And apart from that, one important concept also which we want to see today is regarding the placement of the pressure probes, from which actually we are getting the data of pressure, and then finally we are converting that data into the corresponding velocity field. Okay, so that is the whole idea of today's lecture. So let me start now with one very important type of flow measurement device, which is particularly known as Coriolis mass flow meter. This particular type of flow meter is also known as inertial mass flow meter. Okay, so nowadays it is very popular for the measurement of mass flow rate. So one major difference between the other flow measurement devices, and this is that over here we are actually directly getting the mass flow rate of the fluid medium. Okay, instead of volumetric flow rate we are getting directly the value of mass flow rate. Another advantage of this type of flow meter is that here we will be actually having or we can employ this type of flow meter for measurement of mass flow rate of both liquid as well as gaseous medium. Okay, so we are not having any restriction from the medium point of view. Whether our medium is gas or liquid, we can employ this type of measurement technique for both the fluid mediums. Okay, so the basic idea over here is to employ Coriolis force, uh, which will be actually changing the oscillation dynamics of our mechanical tubing structures while fluid will be flowing inside the tube. Okay, so based on that, we try to actually identify the deflection of the tubes, and then we will be actually measuring or relating the deflection of the tube to the corresponding mass flow rate of the fluid medium. Okay, so basically what I am trying to say, that general structure is we are having some tube structure. So you can see in this particular animation on the left hand side what we are having actually two tubes. So you can see this tube structure is something like a triangle, and you can consider that while fluid will be flowing, flow will be coming from left to right direction, and then this fluid will be flowing inside the tubes, and then through this particular entry we will be having nothing but outlet of the fluid. Okay, so in this particular first animation what I have done, I have actually shown the forced oscillation of the tube medium. So nothing but what we are doing with the help of some external electromechanical arrangement, we are converting electrical signal into the mechanical vibrations of these tubes. So you can see over here both these tubes are actually vibrating. So first tube is going in upward direction and then it is moving in downward direction. So it means these tubes are nothing but having periodic forced oscillations. We are providing some we are having some electromechanical transducer which is actually converting our electrical signal into the mechanical oscillations of these tubes. Okay, so in this very first animation which is there on the left hand side, you can clearly see that we are having very systematic oscillations. Okay, so in this particular tube we are having actually two ends, one is left end and one is right portion of this tube. So in this particular situation you can see both the left as well as the right end of the tube are nothing but having same type of oscillations. Okay, so this is nothing but the natural this is nothing but the forced oscillations of the tube medium when we are not having any fluid flowing inside the tube. So this particular situation is corresponding to the no flow condition. Okay, while fluid is not flowing inside the tube. Then you can consider another situation on the right hand side while fluid is flowing from left direction and it is moving in the rightward direction. Okay, so in this particular this one situation, you can see that we are having the motion of fluid medium inside this particular tube. So you can see now if you just try to see the oscillation pattern of this tube, while this top tube is actually rising in upward direction, this particular right portion of the tube is having actually more upward oscillation, or I should say the more upward displacement, and this left portion is having actually less displacement. While it is moving in downward direction, once again we are having actually the difference of oscillations between the two ends of this particular tube. Okay, so it means what is basically happening, we are nothing but having distortion of the tube. Now if we are able to measure this distortion or this deflection of the tube, in that case what will be happening, we will be able to correlate that deflection of the tube to nothing but the amount of mass flow rate which is actually flowing inside this tube. Okay, so this particular condition is corresponding to the flow of fluid inside the tube. So it means flow of fluid is actually changing the oscillation dynamics of our tube mechanical structure. Okay, so how this is happening, let us try to see. But before that, let us first see what is the basic arrangement of a Coriolis mass flow meter. So in case of an Coriolis mass flow meter, what we will be having, we will be having some mechanical rigid body which will be actually holding these tubes. Okay, and obviously inside this rigid structure we will be having some arrangement which will be uh, connecting these tubes nothing but to the flow of fluid which is coming from this left pipe. Okay, so here we will be having some internal arrangement which will be providing the flow. Now in this particular section you can see over here we are having some driver unit over here. So this driver unit is nothing but it is some electromechanical transducer. Okay, so what it will be doing, we will be supplying some electrical input in the form of electrical energy, and that input will be actually converted into the mechanical oscillations. Okay, so basically this particular driver unit will be providing the forced oscillations to this tube structures. Okay, and then while flow is happening, obviously what will be happening during the flow, as we have seen in the previous picture or previous slide, what we are having nothing but the different displacement of this right portion and left portion of this particular tube. Okay, so what we want to basically measure that how much we are having the deflection. So that deflection we can measure with the help of some sensing element. So for measurement of the deflection of left tube, we are having one sensor element over there and another sensor element we are having for the right side, for the measurement of right portion of displacement of right portion of the tubes on the right hand side. Okay, so another representation is also shown over here. So here you can see clearly that this is something a flange over here, and this in this particular flange we will be having actually the inflow pipe connected over here, and this will actually allow the flow to pass through this sensing tube, and inside this sensing tube we are having some drive coil which will be subjecting this tube to the force oscillations, and then we are having two some arrangements over here. So these are nothing but two peacock coils which will be basically measuring the displacement of this tube structure on left portion and right portion of this tube section. Okay, and we are having over here the direction of flow is also specified. So in this particular direction flow will be taking place, and then we will be having another flange which will be actually connected to our output pipeline. Okay, and in addition one RTD sensor is also placed over here in order to record the temperature of the fluid medium. Okay, so basically this type of temperature measurement may be required while we want to convert the mass flow rate into volumetric flow rate, because at that in that conversion what we have to do, we have to measure the density of our fluid medium at the given condition of temperature and pressure. Okay, now how this difference of oscillations happens on left and right portion of the tube, let us try to see this with the help of this particular schematic arrangement. Okay, so in this schematic arrangement what I am doing, I am considering U section. Now I am considering initially that this U tube is actually, because of the forced this drive coil, whatever we have used, we are considering that, say, uh, in this particular situation, it is actually moving in upward direction. Okay. So while it will be moving in upward direction, during that time, what will be happening? Our direction of angular rotation of this mechanical structure of the tube is nothing but in the counterclockwise direction. So because of that, what will be happening? We will be finding that our omega vector, or I should say the normal direction to the rotation field, will be nothing but in the plane which is normal to this surface of the slide. Okay, so this is nothing but our direction of rotational field, rotational velocity omega. Now flow is happening in this particular direction. So you can see over here, for this particular left portion of the tube, we are having velocity vector in this particular direction. So what is basically happening? This fluid will be having some velocity. So let me write this velocity of the fluid as nothing but equal to v. So for this left portion, okay, of the tube, we will be having nothing but velocity vector in this particular direction, and for this right portion of the tube, we will be having velocity vector in this particular direction. Okay, so this is the velocity vector for this particular portion of the tube. Okay, and for this particular portion, we will be having velocity vector is actually nothing but in this particular direction. Okay, so now what will be happening? We know that our Coriolis force is nothing but equal to 2m times omega cross v. So it is nothing but the cross product of angular velocity into the velocity of the fluid medium. So because of that, what will be happening over here in this particular section, if you apply the right hand thumb rule, so if you nothing but curl the fingers of your right hand from omega direction to this direction of v, in that case what you will be finding, that the Coriolis force will be in downward direction on this right hand side. Okay, so Coriolis force which is acting on the fluid medium, or which is induced inside the fluid medium, that will be nothing but in downward direction, particularly for this rightward tube. Whereas for this left tube, you will be finding that Coriolis force is nothing but in the upward direction. So this is nothing but the Coriolis direction of the Coriolis force which is acting on the fluid medium. Now, if you try to take the reaction force which is acting on the tube material, so you will be finding that on this tube material, which is on the right hand side, your reaction force will be nothing but in the vertical upward direction, and for this particular left portion of the tube, you will be having reaction force in nothing but downward direction. Okay, so what is basically happening? While your tube is actually forced to oscillate in upward direction, during that time, the force which is acting because of the inherent Coriolis nature, Coriolis force which is induced inside the fluid, because of that, whatever the reaction on the structure you are getting on the right hand side, that is actually assisting your tube to move in the upward direction. Whereas the left hand portion of the tube, this force is acting in opposite direction. So obviously over here it will try to actually suppress or mitigate the vertical upward motion of this tube material. Okay, so because of that, what will be happening? Every time while the fluid is flowing, we will be having nothing but the difference in the uh, vertical displacement of right and left portion of this tube. Okay, so because of that, what we will be doing over here, we will be basically measuring the difference of displacement between these two portions of the tube, and that difference of displacement will be nothing but proportional to the mass flow rate of the fluid medium which is flowing inside this tube. Okay, so this is the like entire mechanism from the fluidic point of view, or from the force analysis point of view, that why we are getting the different tube displacement on the left and right portions. Okay, now as we have seen that we will be having different displacement. So now let me write small d as nothing but I am writing that the deflection between the left and right portion, or I can write that it is nothing but the displacement of one particular side of the tube relative to the displacement of the another side. Okay, so this D is nothing but relative deflection or relative displacement between the two portions of the tube. So now what we will be having, we will be having nothing but Coriolis force. I have already specified to you over there. So in this particular case, what will be basically happening over here? Whatever this deflection we will be measuring, that deflection will be nothing but equal to K, where this K is some constant, times F, where F is nothing but our frequency of forced oscillations. So whatever the rate at which we are actually forcing the tube to oscillate, that frequency is nothing but our F times m dot, where this m dot is nothing but mass flow rate of the fluid medium. So you can see over here that our mass flow rate is having direct proportionality relation with that of the deflection, relative deflection of the tube material. Okay, so this is the basic idea which is actually employed for measurement of the mass flow rate of fluid medium in our Coriolis mass flow meter. Okay, now we may have different type of configurations of this tube. So like I have shown you, this particular arrangement is nothing but two tube arrangement. So here we are having twin arrangement, and the shape of the tube is nothing but U-like shape. And in this particular second arrangement, our shape of the tube is like triangular arrangement. Okay, so there are different possible arrangement which are employed in industrial mass flow meter. So you can see over here, one of the arrangement is nothing but D arrangement, while fluid will be flowing in this particular direction. So this will be as our inlet pipe, and this will be nothing but as outlet portion. Okay, then another type of arrangement is actually D-like structure. So while fluid will be flowing in this particular direction and it will be coming out like this. Another arrangement is actually U-type tube. So U-type tube you have already seen. Now then we have triangular arrangement, that also I have shown you in the previous slide. Then we may have helix arrangement. Then we may have even straight tube. So in case of straight tube, what we will be doing? We will be subjecting our tube to this type of oscillations. Okay, so oscillation in upward direction as well as oscillation in the downward direction. So this type of periodic oscillations our straight tube will be subjected to, and now depending upon the mass flow rate of the liquid medium, we will be having difference in amplitude. Okay, and that we can actually relate. Okay, so these are the different tube arrangements which are mainly employed in our industrial Coriolis mass flow meters. Now, these Coriolis mass flow meters are actually subjected to one very important issue. So that type of, in particularly this issue with the Coriolis mass flow meters is referred to as actually decoupling effect. Okay. So while we are measuring the flow over here, what we want, that whatever the oscillations of the tube material are there, our fluid should also follow the same set of oscillations. Okay. However, if in our fluid medium we are not having the perfect homogeneous situation, and for example, we can consider that in our liquid phase, some of the gaseous bubbles are also being entrained. So the entrainment of the bubbles will be actually leading to the inaccuracies in our measurement. So how this will be happening, and for different type of situations, how it will be affecting the level of accuracy, that let us try to see. Okay. So now I'll play this animation over here. So what will be happening over here, you can see this is nothing but twin U-tube type structure over here, and this twin U-tube type structure is actually subjected to the oscillations. Okay, so while it is oscillating, fluid is also flowing inside these tubes. Okay, so now what will be happening, if you see at any cross section, what we are having, this black colored boundary is nothing but the periphery of the tube material, and along this diameter of this tube material, we will be having nothing but the geometric center of the tube material. Okay. Now this green colored pointer over here is nothing but it is the center of gravity of the liquid medium, which is there inside the tube. Okay. So now when we are having perfect single phase flow situation, in that case, what will be happening? We will be having the geometric mean geometric center of this tube material will be actually coinciding with the center of gravity of the fluid medium, and we will be having same type of oscillations in our liquid as well as the tube material. Okay, and we will be getting perfectly accurate measurements over here. While we are having the intrusion of gaseous bubble into our liquid medium, in that case now we may have different situations. So the very first situation we are considering that our liquid medium is having nothing but high viscosity. Okay. So in case of high viscosity liquid medium, now what will be happening? We will be having actually lesser oscillations of the bubbles. So because of that, though we are finding over here that we are having difference in between the geometric center of the tube material and center of gravity of the fluid medium, because this bubble is actually creating the heterogeneity inside our fluid medium, and it is actually shifting the center of gravity of the fluid. Okay, so though we are having this difference in center of gravity and the geometric center of the tube, but because of the high viscosity we will be having very less oscillations of the bubble. So because of that we will be having actually the difference between the two will be very small. Okay, so what will be happening, whatever the measurements we will be doing, though we will be having certain amount of inaccuracies, but the order of inaccuracy will be very small while we are using the high viscosity liquid. In case we are having the low viscosity liquids, inside the low viscosity liquid, what will be having? We will be having the significant oscillations of the bubble. Okay, so because of that, we will be having significant difference in between the geometric center of the tube material, and we will be having and the center of gravity of the fluid medium. So because of that, we will be having significant errors in our measurements. Okay, and apart from that, if we are having even the high frequency oscillations of the bubble medium, in that case the difference will be very large, and we will be getting very inaccurate measurement of the flow rate. Okay, so that is one major disadvantage of Coriolis mass flow meters. That so while we are using the Coriolis mass flow meter for any application, we have to ensure that uh, we are not having any impurities inside our fluid medium. If we are having the impurities, in that case what will be happening, we will be having significant amount of errors in our measurement. Okay, now another type of flow measurement device, it is referred to as magnetic flow meter. So magnetic flow meter is particularly having the applications if our fluid medium is nothing but conductive. So if we are having conductive fluid medium, then only we can employ this type of magnetic flow meters for measurement of the flow rate. These are based on the Faraday's law. So what we will be having, we will be having nothing but force equal to B times, or I should say whatever the output voltage field we will be getting from here, that voltage we will be obtaining is that will be nothing but equal to B times, where B is nothing but our magnetic field flux. So it's the flux of magnetic field, B times L, where L will be the characteristic length. Okay, and in this particular case, while we will be having actually a pipe through which fluid is flowing, we can take the diameter of that pipe as nothing but our characteristic length scale multiplied by u, where u will be representing the mean flow velocity at any particular cross section. Okay, so we will be having this as nothing but our mean flow velocity. So what is basically happening? We are subjecting our pipe inside which the fluid is flowing, we are subjecting our pipe to some magnetic flux. Now while that conductive liquid medium is actually crossing that magnetic field, so what it will be doing, it will be producing some electrical output. Okay, so we will be measuring that amount of electrical output, and that will be nothing but directly related to the amount of the magnetic field for which we are subjecting our pipe material, and the velocity of the flow. Okay, so mean velocity of the fluid. Okay, so now this type of in this type of arrangements, actually we can have two different combinations. So in one of the combination, what we may have non-conductive pipe material, and we will be placing some flush mounted electrodes inside the pipe, which will be actually giving us the output voltage. Okay, so this type of arrangement is employed for the low conductive liquids. So, for example, if we are having water, because in that case, what will be happening? The amount of signal which will be developed, that will be very, very small. So, because of that, we will be considering a non-conductive pipe wall, and we will be having two electrodes over here. So, like this, we will be having two electrodes, and these electrodes will be nothing but flush mounted on the pipe, so that these are actually having physical contact with the conductive liquid. Okay. Then another situation we may have, which can be employed for highly conductive liquids like liquid metals. So in these cases, what we'll be having, we will be having the significant amount of output voltage. So under such circumstances, we can what we can do, we need not to place separate electrode materials. Rather, whatever the pipe wall we are having, that can only be considered as electrode, and we can simply connect wires to this pipe wall in order to take our output signal. Okay, the only limitation of magnetic flow meters is that these will be only working if our medium is nothing but conductive. Okay, then another important method which is used for flow visualization, so that is something which is known as hydrogen bubble based method. Okay, so in this particular method of visualization, the idea is that we will be having some sensor inside our, or I should say, we will be having some arrangement inside our flow field. So for example, if I consider that this is my flow pipeline, and inside this pipeline I have some wire. Okay, and this wire is actually subjected to some electrical voltage. Okay, so what will be happening if the liquid is flowing over here? So what will be happening, for example, if water is flowing over here, so and we are supplying some current over here, so because of this current, what will be happening, we will be having actually this water will be electrolyzing, and it will be producing small hydrogen bubbles over here. So we will be having nothing but the production of hydrogen bubbles. Now once we are having these small hydrogen bubbles inside our flow field, then we can actually illuminate these bubbles with the help of some optical flow visualization based techniques, and then we can try to trace the path of these bubbles in order to visualize our entire flow field. Okay, so this is one electronic circuit which is given over here, and this particular type of electronic circuit is actually employed for generation of the bubble, hydrogen bubble within our fluid medium. Okay, now there are typical arrangements for using this wire for generation of the bubble. So what we are having, we may have one vertical wire arrangement. So in case of vertical wire arrangement, actually the wire will be, axis of wire will be actually normal to the direction of the flow. Okay, so from this particular wire, we will be having generation of large number of bubbles, and then with the help of the optical visualization techniques, we will try to trace the path of these bubbles. Okay, so one important thing we have to consider over here, why, because this wire we will be inserting into or inside our flow field, so this wire should be very thin. So generally what is done, we take the diameter of the wire of the order of 25 to uh, 50 micrometer. Okay, and generally it is actually made up of platinum material. Okay, now another arrangement we may have of horizontal wire probe. So in case of horizontal wire probe, what we will be having, the wire will once again having its axis normal to the direction of the flow, but the wire will be located in horizontal orientation in place of the vertical orientation. Okay, so these are the two different commonly used arrangements which are employed. However, we may have apart from this any other type of arrangement for the measurement of the flow. Okay, now this is one typical flow field which is actually obtained by tracing the path of these hydrogen bubbles. So over here you can see on the left hand side we are having one vertical bubble wire which will be continuously generating the bubble, and then by tracing the path of the bubble actually we can plot the corresponding flow profile. Okay, so this particular flow profile is plotted by um, tracing the path of the bubble at the frequency of 30 kilohertz. Okay, so this is one typical representation which is actually helping us in visualizing the flow field by generating the bubbles, hydrogen bubbles within the flow field. So this will be only applicable for visualizing the flow field inside the liquid medium. Then now one very last topic we will try to see in this particular lecture. So this topic is actually mainly oriented towards the placement of the pressure probes. Okay, because in our very first lecture we have seen the measurement of the flow using the measurement of the pressure. So it means the data of pressure, whatever we are measuring, that should be very correct while we are using that data in order to obtain the corresponding velocity field. Okay, so while we insert different type of pressure probes inside our flow field, now depending upon the orientation of the pressure probe with reference to the direction of the flow, we may have different type of inaccuracies or different type of errors which will be induced in the measurement of the pressure. Okay, so what we will try to do over here, we will try to see that if we are having issues in placing the probes, then what kind of errors we may get into our pressure measurement. Okay, ultimately what will be happening if we are getting the errors in our pressure measurement itself and we are using that inaccurate data for obtaining the corresponding velocity field, ultimately our velocity field will also be incorrect. Okay, so one of the common pressure measurement device is something which I have already introduced to you, that is something which is known as pitot tube. Okay, the basic idea of pitot tube is that if we are having flow happening inside some pipe, what we will be having, we will be having two types of arrangement. One, we will be having the measurement of the static pressure. So this particular type of tap which is located in a direction normal to the direction of the flow, from this we will be getting nothing but our static pressure. Okay, so from here we will be getting the static pressure. Then we will be having one more inserted tube into our flow field, and in this particular tube, what we will be having at this particular junction, we will be having nothing but uh, zero velocity of the fluid medium. So because of that, whatever the kinetic head this fluid particles were having at the immediate vicinity of this tube, that kinetic head will be actually converting into the corresponding pressure field. Okay, so that's why whatever the pressure we will be measuring using this tube, that particular pressure is nothing but known as stagnant pressure. Okay, and it is given by symbol P naught, and this P naught is nothing but static pressure plus dynamic head, where dynamic head will be equal to half rho u square. Okay, so and u is nothing but our flow velocity. Okay, so now what will be happening, so it means our stagnant pressure will always be greater in comparison to the static pressure, so obviously we will be having higher value of the stagnant pressure, and the difference between the stagnant pressure and our static pressure will be actually equal to the dynamic pressure, which can be then employed for measurement of the velocity. Okay, now this is the very basic idea. Now how this idea is actually implemented, so generally when we implement the pitot tube to measure our flow field, what we do, we consider the arrangement of some annular tube based structure. So what we are having, we are having some inner tube, and this particular inner tube basically gives us the measurement of the static pressure, sorry, stagnant pressure. Okay, so this inner tube will be giving us the measurement of nothing but stagnant pressure P naught. Then we have one annular tube outside this particular central tube. So in this annular tube also, what we will be doing, we will be having some arrangement over here. Okay, so we will be having some arrangement over here. So we will be having actually some holes are provided in a direction normal to the direction of the flow. So these holes will be nothing but sensing static pressure inside this annular tube. Okay, so because the placement of the holes is nothing but in a direction normal to the direction of the flow. So that's why whatever the pressure we will be sensing inside this annular tube, that will be nothing but our static pressure. So it means whatever the central tube we are having, we are obtaining the stagnant pressure from the central tube, and we are obtaining the static pressure from this particular annular tube. Okay, then what we can do, we can convert both these tubes to our manometer. So to one end of the manometer we will be connecting our central tube, and to other end of the manometer we can connect our annular tube. Okay, so obviously what will be happening in this particular side, we will be having more pressure. So because of that, our liquid will be rising in this direction. Okay, so this is the head which we can measure, and this particular head will be nothing but the difference of the stagnant pressure and the static pressure, and then this we can equate directly to our dynamic head. Okay, so this is how we generally employ the pitot tube for measurement of the local velocity field. Why I am saying local velocity field? Because if I change the location of the pitot tube to any other location in the radial direction of this tube, so we can actually measure the velocity corresponding to that particular location. Okay, so this is the common idea of using the pitot tube. Now what I will do, I will just describe that if this tube is say located at certain angle from the direction of the flow. So what we want that this tube should be perfectly aligned to the direction of the flow, and whatever the taps we are having for measurement of the static pressure, these should be in a direction normal to the direction of flow. But what we are saying that due to the practical limitations, if we are having errors in placement of the tube, then what sort of inaccuracies will be resulting into our measurement of the pressure, which will be then further translating into the measurement of the velocity field. So that let us try to see. Okay, so what we have done over here in this particular graph, we are actually measuring the error, and this error is nothing but given in terms of the percentage of velocity head. So you can see over here, this is nothing but induced total stagnant pressure which is induced on our pitot tube, and this P naught is nothing but our actual stagnant pressure which could have been uh, obtained if we are having the perfect placement of the tube, and this is measured with relative to the dynamic pressure head. Okay, so you can see over here we are having actually this yaw angle over here. So yaw angle is nothing but if I take the top view of a pipeline. So inside the top view of the pipeline, if I have this a direct alignment of the tube with reference to the direction of the flow, then obviously my angle will be 0. Now if say my tube is actually arranged at certain angle to the direction of the flow, so whatever the angle we are having this theta over here, that we are calling as nothing but our yaw angle. Okay, so now while we are actually using the pitot tube for measurement of the pressure, obviously we are having different type of tube. So one of the simplest arrangement is that we are having simple tube. So this is for example shown over here. So this is our simple pipe like tube arrangement. So in this arrangement, we are considering that if it is actually deflecting at some angle theta from the direction of the flow. So for this type of tubes, what we will be having, we will be having actually the plot of pressure error, which will be varying with the corresponding value of theta that will be following this particular line. Okay, so this is in the negative theta direction, and if we are having the value of theta in positive direction, then obviously we will be having this particular plot applicable. So that is when we are having actually normal circular cross section pitot tube. Okay, now another type of pitot tube arrangement we may have, that instead of using a single tube, what we are doing, we are actually having some small tube like structure, and inside this tube then we are placing one more small tube. Okay, so our actual flow tube is actually a very large tube. Inside that, whatever the pitot tube we are using for measurement of the stagnant pressure, that tube is actually also placed inside some another tube like structure. Okay, so that is this B type pitot tube. So you can see this outer tube is nothing but referring to that external tube which is connected over here, and then inside that we are having our actual tube which is actually measuring the value of the stagnant pressure. So for this type of tube construction, this particular line over here nothing but represent our corresponding error which will be occurring because of the misalignment. Okay. Then in third type of tube, pitot tube, so you can see this is a C-type tube. So in case of C-type tube, what we are having, instead of using a straight tube arrangement, what we are having actually, we are having a wedge-like tube in that. Okay, so initially we will be having some expanded portion, and then we will be having a small constant cross-section tube over there. So this is another type of pitot tube configuration. So for this type of pitot tube configuration, you can see that if you are having even very large angles, then also error introduced will be very less. Okay, why? Because whatever the error which will be coming because of the misorientation, that error will be actually some of that error will be reduced by the flow which will be actually traversing from this wedge section to the constant cross section of the tube. Okay, so that will be actually, this wedge section will be nothing but guiding the flow in proper direction. So because of that, we will be having lesser chances of error over there. Okay. Then apart from that, another arrangement we may have that we are having a tube, and instead of having the hole in the front direction, actually we are creating the hole in some circumferential direction. Okay, so for this type of tube, actually we will be having error plot something like this. And then the very last type of pitot tube, which is particularly known as keel type pitot tube, what we are having, this is the corresponding structure of this type of pitot tube, that we are having this two tube like arrangement as shown in case of B like pitot tube, but the only difference is that whatever this external tube we are using, instead of having a constant cross section, we are actually using Venturi like external tube. Okay, and after that, whatever the pitot tube is actually coming outside, that is also not vertically oriented, it is having certain angle. Okay, so if we are in this type of tube, that is also very helpful in minimizing the errors because of the misorientation with the flow direction. Okay, then as I have already told you that while we will be using the pitot tube for measurement, we will be nothing but having some internal tube which will be giving us the value of stagnant pressure, and then we will be having some outside annular tube, and we will be having some holes on this periphery of this annular tube which will be actually assisting us in obtaining the value of the static pressure. Okay, so basically what happens, this is nothing but our leading edge of the pitot tube, and then this is nothing but the length of the tube, and you can see over here at diameter of 8 times d from the leading edge of the pitot tube, we have actually placed this circumferential hole. So you can see this is the cross section of the tube. So this is nothing but we are having number of number of holes on the circumference of this outer tube over here in order to measure the static pressure. Okay, so what will be happening, the value of static pressure is nothing but a strong function of the distance at which we are actually placing these particular holes. Okay, so now you can see over here for this conical type one, we are having a conical type pitot tube, and another we are having actually blunt edge type pitot tube arrangement. So now x I am considering as the distance from the leading edge, and nothing but the ratio of x by d is plotted over here. So you can see this ratio of x by d is actually 0, 2, 4, 6. So now depending upon the ratio of x by d means the placement of the hole, whether I am placing hole at this particular location or at this particular location, actually we will be having the changes in value of the static pressure. So that particular value of static pressure which will be induced on this annular tube to the actual value of the static pressure, if we take this difference and relatively if we relate it to the dynamic pressure head that is presented over here. So you can see that is presented for two different situations of supersonic and subsonic flow. So this form line is nothing but corresponding to the subsonic flow situation. So you can see that while your distance will be increasing, so with increase in distance, your error value will be actually approaching nothing but close to 0. Okay. Similarly, for the supersonic flow situation also, you can see this dashed line. So this dashed line is also actually approaching to almost zero at sufficient distance from the starting of the pitot tube. Okay, so generally what is done, distance of 8 times of tube diameter is actually considered as the safe distance for locating the holes on the circumferential periphery of the outer tube in order to obtain the accurate measurement of the pressure. Okay, if we are locating the holes very close to the leading edge of the pitot tube, then we will be having chances of errors in our measurement of the static pressure. Okay. And this is the corresponding situation of percentage error in our dynamic pressure. So this is the percentage error in dynamic pressure depending upon the yaw angle. So for different yaw angles, you can see the if our yaw angle is actually having mm, uh, our value of yaw angle is increasing, corresponding to that the errors in our static pressure will be increasing, whereas in case of stagnant and dynamic pressure, it will be actually initially for the very small values of the yaw angles, the errors introduced will be very less, and later on actually it will be nothing but giving us some underestimate in the dynamic pressure. Okay. Then this particular situation once again refers to the value of static pressure error. So this is nothing but the error in our static pressure, and over here we are referring to the variation of the static pressure with yaw angle. Okay, so this is also given for three different type of pitot tube. So one is for cone type pitot tube, then wedge type pitot tube, and third is Prandtl tube. So in case of Prandtl tube, means we will be having some inner tube and then outer tube at which we will be having this particular holes on the circumferential periphery. Okay. So over here we are nothing but saying that if our axis of the tube is oriented at certain angle from the direction of the flow, then what type of errors or will be introduced into our static pressure measurement, that is actually quantified over here. Okay. Then this is nothing but the errors introduced inside the static pressure measurement when we are having actually, particularly these errors are because of the value of the Mach number. Okay, so if our Mach number is very small, in that case what will be happening, we will not be having significant variations inside the errors. However, corresponding to large value of the Mach number, we will be having actually variation in error. So generally the idea is that if we are having certain error in our measurement of the static pressure with increase or at different values of the Mach number, that error will be remaining almost constant. However, for some specific type of pitot tube geometries, we may have chances of increase or decrease of that error depending upon the value of the corresponding value of Mach number, particularly at high range of the Mach number. Okay, so this curve is very important. Why it is important? Because when we will be using the pitot tube for measurement of flow or measurement of pressure up to the Mach number of 0.6, in that case, irrespective of the type of pitot tube, we can actually use a constant value to correct our pressure. Okay. However, when we are going beyond the Mach number value of 0.6, then obviously whatever the correction factor we are using in order to correct the value of the pressure, that correction factor will be actually nothing but a function of the Mach number. Okay. Then one important point I would like to highlight over here, and this particular point is actually applicable for the supersonic flow situations. Okay, so in case of supersonic flow situation, when we will be having the obstruction of the pitot tube or in front of the flow field, then obviously we will be having nothing but the generation of the shock wave. Okay, so obviously we know that in one side of the shock wave we will be having high density, and on other side of the shock wave we will be having low density. So because of that, what will be happening, you can see over here this P naught tube, because our pitot tube is now connected to this particular portion, means on the low density side of the shock wave. So because of that, what will be happening, from the pitot tube, whatever the value of the stagnant pressure we will be getting, or I should say whatever the value of pressure we will be getting, this pressure I am calling as impact pressure. Why I am calling as impact pressure? Because it is nothing but immediately at the impact point of the pitot tube. Okay, So from here, whatever the value of this impact pressure we will be getting, that will not be equal to the value of the stagnant pressure in the far field. Okay. So what we have to do, we have to actually correct the value of the pressure with the help of some correlation. So that is given over here. So you can over here nothing but correct the value of free stream pressure, or I should say the far field pressure, with the help of this impact pressure. So your pitot tube will be giving you P naught 2. Now using this value of 2 gamma divided by gamma plus 1 into Mach number 1 square. So Mach number value in this particular zone, it will be greater than 1, and in this particular zone our Mach number will be actually having different value, because over here obviously we will be having actually different density of the surrounding fluid medium. Okay, so because of the change of the density, the corresponding value of Mach number on left hand side of the shock wave and on right hand side of the shock wave will be actually changing. So the by considering the corresponding relationship in between the Mach numbers, but more importantly what we want to do, because we want to obtain the far field pressure, so that's why the Mach number also, whatever we will be obtaining, that will be nothing but our far field Mach number. Okay, so by using the ratio of Cp by Cv for a particular type of the fluid medium which we are having, and the corresponding value of the Mach number, actually we can relate our impact pressure to the far field pressure field. Okay, so that is one very important point. This correction equation actually we have to employ for measurement of the actual free stream pressure while we are having the occurrence of the supersonic flow. Okay, so now what I will do, I will now with this conclude our discussion on the measurement of flow, and from our next lecture onwards we will start our discussion on the measurement of temperature. Okay.